All right, so this is, we're talking about 9.3 part 2. All right. P series. They have the form. The sum n equals 1 to infinity of 1 over n to the p. And I'll just write out a few terms. So we get 1 over 1 to the p plus 1 over 2 to the p plus 1 over 3 to the p plus dot, dot, dot. And here we're saying, this is important, p is a positive constant. So we're saying p is positive here. Now, if we have, if p equals 1, what do we have? Harmonic series. Which we already know diverges. We showed that the harmonic series, we showed directly that the harmonic series diverges. We can use the integral test to show what other cases give us convergence or divergence for p series. So I'm going to give you the cases now, and then we'll show how the integral test gives us this, how this the convergence or divergence of p series comes from the integral test. So p series converge if p is greater than 1, and diverge. Oh, sorry, I said 1 and I wrote 0, didn't I? 0, 1, they're pretty close, right? They diverge if 0 is less than p less than 1, less than or equal to, because they diverge for the harmonic series.
It doesn't have to be an integer, right?
No, just positive. So if p is some kind of fraction, then our harmonic series diverges. Fraction less than 1. So it's a nice, easy test as long as your series has this one specific form. Let's use the integral test to show this. All right, so I'm going to say that f of x is 1 over x to the p. And again, we're saying p is positive, greater than 0. Is this function positive?
Yes.
And continuous if x is greater than or equal to 1?
Yes.
Okay? So we have positive, continuous for x greater than or equal to 1. Now we need to show, is it decreasing? F prime, we'll take the derivative. F prime, nice easy derivative to take, negative p over x to the p plus 1. Well, if p is positive, negative p is negative. So this is less than 0 for x greater than or equal to 1. So the integral test applies. We had to make sure that we could apply the integral test first. All right, so we're going to integrate now. We're going to say the integral from 1 to infinity of 1 over x to the p. And I'm going to rewrite this dx equals the integral from 1 to infinity of x to the minus p dx. And for our improper integral, it's going to be the limit as b approaches infinity. And want to integrate x to the minus p. What do I get? x to the minus p plus 1, and then we have to divide by minus p plus 1. And we're going to integrate that on 1 to b. And I'm going to rewrite this now. We want to evaluate this. So this equals, and I'm going to pull out this factor. This is constant, doesn't change. And I'm going to write it as 1 minus p. So 1 over 1 minus p times the limit as b approaches infinity of x to the, and I'm going to write this as 1 minus p. And we're evaluating that on 1 to b. So that's 1 over 1 minus p times the limit as b approaches infinity of b to the 1 minus p minus, and when we evaluate this at 1, what do we get? 1. All right. If p is greater than 1, so if p is greater than 1, 1 minus p is positive or negative? Negative. 1 minus p is less than 0. And so this limit, as b approaches infinity of b to some negative exponent, is 0. And so our integral evaluates to negative 1 over 1 minus p, or 1 over p minus 1. Which is finite. So the series, the integral converges, so the series converges. If 0, so this is our second condition, 0 less than p less than 1, so if p is some fraction between 0 and 1, what is 1 minus p? Positive. 1 minus p is greater than 0. So this limit, then we have limit as b approaches infinity of b to some positive exponent. That limit then doesn't exist. So I'm going to say dne. So the series diverges. And the case where p equals 1, that's the harmonic series. We treated that kind of as a special case, and we proved that directly. So these are how we use the integral test to show our rules for p series. All right, questions? All right, let's look at a couple of examples, and these might be a little different examples than you might have been expecting. Not necessarily a direct application of the p series. We want to find positive values of p we don't want to just repeat verbatim what you did last year. We want to go beyond that. Values of p for which the series converges. So here's the first one we're going to look at. The sum n equals 1 to infinity of n over 1 plus n squared to the p. So we want to find the values of p for which a series like this is going to converge. So if you were going to apply a test, if this were just some number, p were some number, and you were going to apply a test, what test would you apply? We'd apply the integral test, right? Ratio test is for power series. That's when you have a variable in your series. Ratio test is for power series. So we could apply the integral test, right? Because if u is 1 over, or u is 1 plus n squared, du is 2n. So we're going to apply the integral test. It takes a little work, though. Is this for x greater than 1? Is this positive? Yes, because p is a positive value. All of these are going to be positive. So I'm just going to say positive. Check. Is it continuous for x greater than or equal to 1? Yes. We're not going to end up with a divide by 0. Check. Decreasing. Oh.
Sure.
How could we show that this is decreasing? Take the derivative. F prime. If we want to apply the integral test, we have to show that it's decreasing. I'm going to move over because I need a little more room. F prime. We need to use the quotient rule. 1 plus x squared to the p times the derivative of this minus x times the derivative of this. So what do we get when we take the derivative of this? P times 2x times to the p minus 1 over, and we're going to 1 plus x squared to the 2p. Not quite yet. Not quite yet. What are we going to do here?
Take the top equals or less than
Can we get rid of a factor of 1 minus x squared to the p? Because we have a 2p here, we have a p here, and we have a p times this 1 plus x squared to the minus 1?
Probably something
Yeah.
like that.
So I can write this as, so this cancels. I get 1 minus 2x squared p times 1 plus x squared to the minus 1 over 1 plus x squared to the p. Now, for x greater than 0, is this positive?
Yeah.
Yes, p is positive. This is positive. This is this for x greater than 1. This is positive. This is positive. We are multiplying it by 2. We're multiplying it by some other constant. So this is, we're subtracting it from 1. So that's going to be negative.
Negative.
Couldn't we just sketch a graph and demonstrate
That would decrease it. You could show it's decreasing for the range of the graph. For the extent of the graph, it might all suddenly go. All right. So we have now demonstrated that we can apply the integral test. Now we can say. Now we have to take the integral.
Why?
we're going to take the limit as b approaches infinity. We have 1/2 the integral of du over u to the p, right? Where u is 1 plus x squared. So this is 1/2 the limit as b approaches infinity of 1 over 1 minus p u to the 1 minus p evaluated on 1 to b. And what did we just find out about this?
That
if it's greater than 1,
something about
minus 1 or 0. But if it's between 0 and 1, then the limit is minus 0.
Right, if it's between 0 and 1, it's going to diverge. It's going to converge if
Greater than 1.
p is greater than 1. By the same argument we just used.
Why couldn't we have just said this at the very beginning?
Because this is not a p series.
Wait, how did you get there?
P series looks like this. Yes.
How did you get there from that? Can you explain that last
You just like jump like
He
This-
jumped from use of. He didn't use of.
Which part?
Thanks, Dylan.
Here?
I'm going,
Yeah.
I'm going to there.
This is the exact same integral that we just did on the last page.
Oh,
For the p series. This integral is the exact same one we just did, and we found out that converges when p is greater than 1. This is from here over, that's the exact same thing we had on the last page when we showed that when the p series converged. All right, so what we've just done is prove something about kind of a generalized p series. So we can think of something where we have a quantity in the denominator to a p, positive p constant, and the derivative in the numerator. That's going to converge by a similar argument. It's kind of a generalized p series.
do you have to specify that that's the case? Or you just know that it is behind that?
We can't know anything. Anything is anything. We always have to show it.
But we know some stuff.
Some stuff.
So then why can't we just know this stuff?
Well, all we know now is for this specific case.
So for other cases, it's not going to be always the same.
It depends on the form of the thing you have.
Okay.
So this is just the disguise to make us take on
Yeah, well, and to see that we can apply the ideas. Let's listen up. We can apply the ideas about convergence of p series to other kinds of series. We can use this argument that we used for other kinds of series. So this argument we didn't. Well, let me put this way. I was going to say we didn't do the argument on the other page just for fun. We did it so that we could. But I'll say I didn't do it just for fun. I did it so that I could show that we can use it in other situations. The same argument. So the example is not necessarily about this p series, but it's about the argument that we used to show that it converged, because that's a nice argument. All right, let's look at another example. This one might be different. How about this? Same thing. We want to find positive values of p for which this series converges. Three over p to the n. Well, what does this look like? This looks geometric. So this is.
So we have to use that little testing rule.
I'm going to say geometric-ish.
Geometric-ish.
So this is, the other one was p series-ish. This is geometric-ish. So what do we need here?
Don't we set it up where it's like since we know that 3 over p is the r value of our geometric-ish thing, we set up an inequality where it's -1 greater than or equal to 3 over p greater than or equal to.
And okay, so hang on, listen up. So if we're specifying that p is positive,
Oh, we don't even need the -1.
Then we don't need a negative 1. All we need is that
P has to
3 over p is less than 1. So p has to be greater than 3. If we want p to be negative,
second side inequality.
I'm going to say positive or negative. All we need is the absolute value of p to be greater than 3. And then this series would converge. All right. So we can use arguments that we've used before to show convergence or divergence of a specific kind of series to apply to other kinds of series. And we saw that there was an example of that on the quiz. And for later in the chapter, we're going to do that with other kinds of series. We're going to find series representations for various functions using things that we know about other series. All right. Now I have some questions. Which test would we use? What test would we use to decide if that thing converges or diverges?
Integral test.
Is that just the end or?
Just 3n.
Nth term test.
Well, the nth term approaches 0,
I'm doing it.
so that doesn't tell us anything.
But then,
So what someone said, yeah, we can use the integral test. If u is 3x minus 2, du is just 3. So squeeze theorem is for sequences. So we could possibly use the squeeze theorem on the sequences of partial sums. Later on, we will show that this is, we'll call this general harmonic series, and we'll show that the general harmonic series diverges. But we don't have the tools yet quite to do it. How about this one? N equals 1 to infinity of 1 over n 4th root of n.
wait, that's one more.
Geometric. Well, you can turn those into fractional powers, multiply them, and
Wait, that's
then factor that out.
P-series.
So what would be an easier way to say it's a p series, Ben?
1 over n to the power. Yeah, that's right.
This is 1 over n to the 5/4.
Which is very
Wait, isn't that just that's geometric? Or and say it's a series first.
It's a P series.
Geometrically 5/4.
To the 5/4 to the n. So this is a p series.
Convergence.
What does P stand for?
And that's bad. And that one is acceptable.
P is greater than 1. So this converges. How about this one?
The first one was integral test.
Geometric. That's just geometric.
This is geometric.
And that's
Geometric, R is 2/3, so less than 1 converges. How about this one?
They're all P series. P series is just the series that are test. And divided by the square root of n squared plus 1.
Integral test.
This would be integral test, or
Exactly.
You have to do
Freaks
tricks.
up.
or
P series.
isn't that this with p equals 1/2?
Yeah, P series.
and then you can just demonstrate it.
Right. We just showed that series, when that series diverges or converges, where p this is an example where p is 1/2. So that's kind of our generalized p series. So What do we know? P is less than 1. Diverges for a P series, yes. You could say this is like the example, something like the example in class with P such and such that diverges or converges. Yes. So now that we showed that, you can use that as a test. So it's this kind of a generalized P series. Yes. Okay.
So, oh, for the P series, do we have to show the conditions like the integral test, or no? Is that just
We've already shown it. So now we know that. Yeah. Well, I've shown it, so we know it. All right. How about this one? Be careful.
Oh, e to the, no, yeah, e to the 1, it's just e.
E to the x?
No, e to the 1.
E to that 1.
Oh wait, no, that's the sequence.
That's a sequence. That's a limit.
It converges to E as a sequence. And
So it diverges.
Diverges why?
Because
R is greater than 0.
Not geometric, but you're on the right track. What did you say, Connor? Connor? What'd you say?
Oh,
Why?
Well, the limit as n approaches infinity of the sequence is e to the 1, which is e, and that does not equal 0, so it diverges.
Couldn't you also draw that as geometric-ish, and if n equals greater than 1, always adding something. When you're saying it's 1, you want something which is always greater than 1. It would fail the geometric test too.
It's not exactly geometric because for geometric you have a constant raised to an exponent.
So you're not allowed to use the logic of that saying.
No. But this is a nice argument.
That's
Last one. 1 over n natural log n to the 3rd power. Sam says integral test. You are going to say integral test. U equals ln n. Du equals 1 over n.
Couldn't you also do a P series because it's a function and its derivative? Because you got ln and the derivative of ln is 1 over n.
Now for this one we would have to, so we showed that, so this is where we'd have to be careful. For this type of series, we showed that this is decreasing. We'd have to do some work to show that this was decreasing.
But if I give you that,
Yeah. I would accept that argument,
you
yes.
can't do integral test though because ln of 1 is 0, right?
Oh. All right, so that was a good point. Trent said I had written n equals 1 to infinity. This is undefined at n equals 1. So I would need to do 2 to infinity. Did you say that too, Sam? Did you say that, Sam?
No, you just said to.
No? Okay. I thought I missed it. So we need, so that was a nice catch.
But so if I could show that it was decreasing, I could
Yeah, and then it would satisfy the conditions of that other type of series.
for integral test, don't you have to find that it's
Yeah, you have to find it anyway.
So if I find that it's decreasing, then I can just say, hey,
By the example we did in class, this would diverge because P is, or converge because P is greater than 1. Yeah. Yeah.
I'm still really upset by the one above this, why you can't use the geometric argument, because 1 plus 1 over
Well, you-
n is always greater than 1.
Okay, so you could do that.
Oh, I could do
Yeah,
that.
you could say 1 plus 1 over n is greater than 1. So this series is greater than 1 to the n. Everywhere, so yeah. Right. Geometry, yes. You could say that. Yes. So term by term, it's larger than a,
Well, that's what I was getting.
and but technically we haven't learned that test yet, but we'll talk about that next time. Direct comparison.
Oh, yeah, where you might say, well, it looks like this. So.
Yeah. All right. Yes.
you show that one is decreasing.
Take the derivative.
Take the derivative.
Yeah. It's not too bad. It's not too bad.
Be done.
There we go.